Cloud computing can be defined as a new style of computing in which dynamically scalable and often virtualized resources are provided as a services over the Internet. Cloud computing has become a significant technology trend, and many experts expect that cloud computing will reshape information technology, processes, and the IT marketplace. With the cloud computing technology, users use a variety of devices, including PCs, laptops, smartphones, and PDAs to access programs, storage, and application development platforms over the Internet, via services offered by cloud computing providers. Advantages of the cloud computing technology include cost savings, high availability, and easy scalability. Cloud is therefore a parallel and distributed computing system consisting of a collection of interconnected and virtualized computers that are dynamically provisioned and presented as one or more unified computing resources based on service-level agreements, SLA, established through negotiation between the service provider and consumers. Simply put, they are hardware-based services offering compute, network, and storage capacity where hardware management is highly abstracted from the buyer. Buyers incur infrastructure costs as variable OPEX, and infrastructure capacity is highly elastic. The National Institute of Standards and Technology, NIST, characterizes cloud computing as a pay-per-use model for enabling available, convenient, on-demand network access to a shared pool of configurable computing resources, e.g. networks, servers, storage, applications, services, that can be rapidly provisioned and released with minimal management effort or service provider interaction. The roots of cloud computing can be tracked by observing the advancement of several technologies, especially in hardware, virtualization, multi-core chips, Internet technologies, web services, service-oriented architectures, Web 2.0, distributed computing, clusters, grids, and systems management, autonomic computing, data center automation. As you can see in the diagram, starting from the top, in Phase 1 to Phase 6 in these computing generations, it looks like that cloud computing is a return to the original mainframe computing paradigm. However, these two paradigms have several important differences. Mainframe computing offers finite computing power, while cloud computing provides almost infinite power and capacity. In addition, in mainframe computing dummy terminals acted as user interface devices, while in cloud computing powerful PCs can provide local computing power and caching support. Cloud computing can be viewed as a collection of services, which can be presented as a layered cloud computing architecture. Services offered through cloud computing usually include IT services referred as to SaaS, software as a service, which is shown on top of the stack. SaaS allows users to run applications remotely from the cloud. Infrastructure as a service, IaaS, refers to computing resources as a service. This includes virtualized computers with guaranteed processing power and reserved bandwidth for storage and Internet access. Platform as a service, PaaS, is similar to IaaS, but also includes operating systems and required services for a particular application. In other words, PaaS is IaaS with a custom software stack for the given application. The data storage as a service, DSaaS, provides storage that the consumer is used, including bandwidth requirements for the storage. The main types of cloud computing are public cloud, where a third-party cloud service provider owns and operates the cloud, providing computing resources like storage and servers over the Internet. Microsoft Azure is an example of a public cloud. Private cloud is where a single business or organization uses the cloud computing resources exclusively. A private cloud can be located on the company's own data center or hosted by a third-party service provider. Hybrid cloud is a combination of public and private clouds that allows data and applications to be shared between them. A cloud platform offers an environment on which developers create and deploy applications and do not necessarily need to know how many processors or how much memory that applications will be using. In addition, multiple programming models and specialized services, e.g., data access, authentication, and payments, are offered as building blocks to new applications. Applications reside on the top of the cloud stack. Services provided by this layer can be accessed by end users through web portals. Therefore, consumers are increasingly shifting from locally installed computer programs to online software services that offer the same functionality. Traditional desktop applications such as word processing and spreadsheet can now be accessed as a service in the web. This model of delivering applications, known as software as a service, SaaS, alleviates the burden of software maintenance for customers and simplifies development and testing for providers. IaaS is a cloud computing model where a service provider delivers fundamental computing resources, such as servers, storage, and networking, over the Internet. These resources are provisioned on demand and can be scaled up or down as needed. These are some of the primary features of the cloud. Self-service. Clouds must allow self-service access so that customers can request, customize, pay, and use services without intervention of human operators per usage metering and billing. Cloud computing eliminates upfront commitment by users, allowing them to request and use only the necessary amount. Services must be priced on a short-term basis, e.g., by the hour, allowing users to release, and not pay for, resources as soon as they are not needed. Elasticity. Cloud computing gives the illusion of infinite computing resources available on demand. Therefore, users expect clouds to rapidly provide resources in any quantity at any time. In particular, it is expected that the additional resources can be a. Provisioned, possibly automatically, when an application load increases, and b. Released when load decreases, scale up and down. Customization. Resources rented from the cloud must be highly customizable. Customization means allowing users to deploy specialized virtual appliances and to be given privileged, root, access to the virtual servers. Key technologies that enabled cloud computing are virtualization, web service and service-oriented architecture, service flows and workflows, and Web 2.0 and mashup. Let us understand each one separately. The advantage of cloud computing is the ability to virtualize and share resources among different applications with the objective for better server utilization. In non-cloud computing, 3 independent platforms exist for 3 different applications running on its own server. In the cloud, servers can be shared, or virtualized, for operating systems and applications, resulting in fewer servers. Web services and service-oriented architecture, SOA, are not new concepts, however they represent the base technologies for cloud computing. Cloud services are typically designed as web services, which follow industry standards including WSDL, SOAP, and UDDI. A service-oriented architecture organizes and manages. The concept of service flow and workflow refers to an integrated view of service-based activities provided in clouds. Workflows have become one of the important areas of research in the field of database and information systems. Web 2.0 refers to a second generation of the World Wide Web that emphasizes user participation, collaboration, and sharing of information. It's characterized by dynamic content, user-generated content, and rich user experiences. Key features include user-generated content, UGC, sharing, dynamic content, collaboration, and rich user experiences. Facebook, Twitter, and Instagram are typical examples. A mashup is a web application that combines data and functionality from multiple sources to create a new service or application. It's like a remix of different online resources, integrating them in innovative ways. A key challenge IaaS providers face when building a cloud infrastructure is managing physical and virtual resources, namely servers, storage, and networks, in a holistic fashion. The orchestration of resources must be performed in a way to rapidly and dynamically provision resources to applications. The software toolkit responsible for this orchestration is called a Virtual Infrastructure Manager, VIM. This type of software resembles a traditional operating system, but instead of dealing with a single computer, it aggregates resources from multiple computers, presenting a uniform view to user and applications. A key challenge IaaS providers face when building a cloud infrastructure is managing physical and virtual resources, namely servers, storage, and networks, in a holistic fashion. The orchestration of resources must be performed in a way to rapidly and dynamically provision resources to applications. The software toolkit responsible for this orchestration is called a Virtual Infrastructure Manager, VIM. This type of software resembles a traditional operating system, but instead of dealing with a single computer, it aggregates resources from multiple computers, presenting a uniform view to user and applications. Virtualization support. The multi-tenancy aspect of clouds requires multiple customers with disparate requirements to be served by a single hardware infrastructure. Virtualized resources, CPUs, memory, etc., can be sized and resized with certain flexibility. These features make hardware virtualization the ideal technology to create a virtual infrastructure that partitions a data center among multiple tenants. Self-service, on-demand resource provisioning. Self-service access to resources has been perceived as one of the most attractive features of clouds. This feature enables users to directly obtain services from clouds, such as spawning the creation of a server and tailoring its software, configurations, and security policies, without interacting with a human system administrator. This capability eliminates the need for more time-consuming, labor-intensive, human-driven procurement processes familiar to many in IT. Multiple back-end hypervisors. Different virtualization models and tools offer different benefits, drawbacks, and limitations. Thus, some vManagers provide a uniform management layer regardless of the virtualization technology used. This characteristic is more visible in open-source vManagers, which usually provide pluggable drivers to interact with multiple hypervisors. In this direction, the aim of libvirt is to provide a uniform API that vManagers can use to manage domains, a VM or container running an instance of an operating system, in virtualized nodes using standard operations that abstract hypervisor-specific calls. Dynamic resource allocation. Increased awareness of energy consumption in data centers has encouraged the practice of dynamic consolidating VMs in a fewer number of servers. In cloud infrastructures, where applications have variable and dynamic needs, capacity management and demand prediction are especially complicated. This fact triggers the need for dynamic resource allocation aiming at obtaining a timely match of supply and demand. Energy consumption reduction and better management of SLAs can be achieved by dynamically remapping VMs to physical machines at regular intervals. Machines that are not assigned any VM can be turned off or put on a low power state. In the same fashion, overheating can be avoided by moving load away from hotspots. Virtual clusters. Several vManagers can holistically manage groups of VMs. This feature is useful for provisioning computing virtual clusters on demand, and interconnected VMs for multi-tier Internet applications. High availability and data recovery. The high availability (HA) feature of vManagers aims at minimizing application downtime and preventing business disruption. A few vManagers accomplish this by providing a failover mechanism, which detects failure of both physical and virtual servers and restarts VMs on healthy physical servers. This style of HA protects from host, but not VM, failures. For mission-critical applications, when a failover solution involving restarting VMs does not suffice, additional levels of fault tolerance that rely on redundancy of VMs are implemented. In this style, redundant and synchronized VMs, running or in standby, are kept in a secondary physical server. The HA solution monitors failures of system components such as servers, VMs, disks, and network and ensures that a duplicate VM serves the application in case of failures. Data backup in clouds should take into account the high data volume involved in VM management. Frequent backup of a large number of VMs, each one with multiple virtual disks attached, should be done with minimal interference in the system's performance. In this sense, some vManagers offer data protection mechanisms that perform incremental backups of VM images. The backup workload is often assigned to proxies, thus offloading production server and reducing network overhead. Cloud computing. It is a techno-business disruptive model of using distributed large-scale data centers, either private or public or hybrid, offering customers a scalable virtualized infrastructure or an abstracted set of services qualified by service-level agreements, SLAs, and charged only by the abstracted IT resources consumed. Most enterprises today are powered by captive data centers. In most large or small enterprises today, IT is the backbone of their operations. Invariably, for these large enterprises, their data centers are distributed across various geographies. They comprise systems and software that span several generations of products sold by a variety of IT vendors. In order to meet varying loads, most of these data centers are provisioned with capacity beyond the peak loads experienced. If the enterprise is in a seasonal or cyclical business, then the load variation would be significant. Thus, what is observed generally is that the provisioned capacity of IT resources is several times the average demand. This is indicative of significant degree of idle capacity. Many data center management teams have been continuously innovating their management practices and technologies deployed to possibly squeeze out the last possible usable computing resource cycle through appropriate programming, systems configurations, SLAs, and systems management. Cloud computing turned attractive to them because they could pass on the additional demand from their IT setups onto the cloud while paying only for the usage and being unencumbered by the load of operations and management. Invariably, migrating into the cloud is driven by economic reasons of cost cutting in both the IT capital expenses, CapEx, as well as operational expenses, OpEx. Department of CSE 30, PAGEAY 2023-2024 Cloud Computing. If the average costs of using an enterprise application on a cloud is substantially lower than the costs of using it in one's captive data center, and if the cost of migration does not add to the burden on ROI, then the case for migration into the cloud is strong. Apart from these costs, other factors that play a major role in the cloudonomics of migration are the licensing issues, for perhaps parts of the enterprise application, the SLA compliances, and the pricing of the cloud service offerings. These are the 7 steps of migration. Assessment. Proof of concepts are prototypes for various approaches to the migration, along with the leveraging of pricing parameters enables one to make appropriate assessments. These assessments are about the cost of migration as well as about the ROI that can be achieved in the case of production version. The next process step is in isolating all systemic and environmental dependencies of the enterprise application components within the captive data center. This, in turn, yields a picture of the level of complexity of the migration. Mapping. Generating the mapping constructs between what shall possibly remain in the local captive data center and what goes onto the cloud. Re-architect. A substantial part of the enterprise application needs to be re-architected, redesigned, and re-implemented on the cloud. Augment. Leverage the intrinsic features of the cloud computing service to augment our enterprise application in its own small ways. Test. Validate and test the new form of the enterprise application with an extensive test suite that comprises testing the components of the enterprise application on the cloud as well. Optimize. These test results could be positive or mixed. In the latter case, we iterate and optimize as appropriate. After several such optimizing iterations, the migration is deemed successful. Another important pillar in cloud is virtualization, which is a fundamental technology that underpins the capabilities of cloud computing. It allows for the efficient allocation and utilization of physical resources, such as servers, storage, and networking components. Here's why virtualization is crucial in cloud environments. 1. Resource optimization. 2. Flexibility and scalability. 3. Cost efficiency including pay-as-you-use. 4. Improved disaster recovery. 5. Enhanced efficiency and management. 6. Increased agility. In conclusion, virtualization is a cornerstone of cloud computing, providing numerous benefits such as resource optimization, flexibility, cost efficiency, improved disaster recovery, enhanced efficiency, and increased agility. By leveraging virtualization, businesses can maximize the value of their cloud investments and achieve greater operational efficiency and competitiveness. Anika is a .NET-based service-oriented resource management and development platform. Each server in an Anika deployment, dubbed Anika Cloud Node, hosts the Anika container, which provides the base infrastructure that consists of services for persistence, security, authorization, authentication and auditing, and communication, message handling and dispatching. Cloud nodes can be either physical server, virtual machines, Xen Server and VMware are supported, and instances rented from Amazon EC2. The Anika container can also host any number of optional services that can be added by developers to augment the capabilities of an Anika cloud node, thus providing a single, extensible framework for orchestrating various application models. Microsoft Azure Cloud Services offers developers a hosted .NET Stack, C#, VB.NET, ASP.NET. In addition, a Java and Ruby SDK for .NET services is also available. The Azure system consists of a number of elements. The Windows Azure Fabric Controller provides auto-scaling and reliability, and it manages memory resources and load balancing. The .NET Service Bus registers and connects applications together. The .NET Access Control identity providers include Enterprise Directories and Windows Live ID. Finally, the .NET Workflow allows construction and execution of workflow instances. In conjunction with the Salesforce.com service, the Force.com PaaS allows developers to create add-on functionality that integrates into main Salesforce CRM SaaS application. Force.com offers developers two approaches to create applications that can be deployed on its SaaS platform: a hosted Apex or Visualforce application. Apex is a proprietary Java-like language that can be used to create Salesforce applications. Visualforce is an XML-like syntax for building UIs in HTML, Ajax, or Flex to overlay over the Salesforce-hosted CRM system. An application store called AppExchange is also provided, which offers a paid and free application directory. Heroku is a platform for instant deployment of Ruby on Rails web applications. In the Heroku system, servers are invisibly managed by the platform and are never exposed to users. Applications are automatically dispersed across different CPU cores and servers, maximizing performance and minimizing contention. Heroku has an advanced logic layer that can automatically route around failures, ensuring seamless and uninterrupted service at all times.